Now let us look at some variations of the derivative theorem that we have stated. The first one is for jump discontinuity of ft at a point t equal to t1. So a jump discontinuity, we know that we assume that ft is piecewise continuous. So then our graph of f might look something like this. So at some points it has discontinuities because the limit from the left does not include the limit from the right, and here also the limits do not agree. So these are the points of discontinuity, but still the left and right hand side limits exist and they are finite. So these points are called jump discontinuities. So here we are assuming that f has jump discontinuity only at one point t equal to t0, which means that it looks something like this. So it is assumed to be continuous over all of r, all of 0 infinity, but at one point it is it has a jump discontinuity. So this is our case A, the first case for f of t. The second one is that f itself is discontinuous at t equal to 0, but the limit when you take, so f of 0 plus here is simply the limit as t tends to 0 plus, so t goes to 0 from the right of ft. This limit exists, but the function itself is not continuous at t equal to 0. So for example, an example of a function which has discontinuity at t equal to 0 and yet that the limit as t tends to 0 from the right ft exists is given by the following function. So you can take ft to be sin t over t for t positive and 0 for t equal to 0. So now note that when you take the limit as t tends to 0, limit as t tends to 0 from the right ft, this is 1 because this is just the limit of sin t over t, which is different from f of 0. So there is a point of discontinuity at t equal to 0. The third option, the third variation is for higher derivatives of f. So we want to compute the Laplace transform of the nth derivative of f. We have already computed the first derivative and we will look at higher derivatives of f. So let's do the first one. So assume that f is continuous on 0 infinity except at t equal to t1, where it has a jump discontinuity, and f prime t exists as a piecewise continuous function on the whole interval 0 to infinity. Now here there is a subtle point, which is that if f has a discontinuity at t equal to t1, then what is the value, what is f prime of t1? The answer is that this is not defined because it is not differentiable at t equal to t1, but the left hand side limit t goes to t1 minus f prime t exists, and limit goes to t1 plus f prime t also exists because it's assumed to be piecewise continuous. So we are only asking the question, what is f prime of t1 at the point t1. Now just to make it piecewise continuous, we can give an arbitrary finite value can be given for f prime of t1, which makes it a piecewise continuous function on the whole interval 0 to infinity. So for this, the formula for the Laplace transform of f prime t is given by S of Laplace transform of ft and minus f of 0 minus e to the power minus t1s f of t1 plus minus f of t1 minus. So note that this is the jump at t1 at t equal to t1 for the function f. So in general, so this is for only one point of discontinuity t equal to t1. In general, if f has finitely many jump discontinuities at t equal to tk, k equal to 0, 1 up to, so 1, 2 up to m say, and all these tk's are greater than 0 for all k, and we keep our assumptions for f. So f is continuous on 0 infinity minus this union of the points tk, k equal to 1 to m, and of exponential order alpha, and f prime t exists as a piecewise continuous function on the whole interval 0 to infinity. Again, we have to give arbitrary finite values of f prime of t1, f prime of t2, etc. up to f prime of tk to make it a piecewise continuous function on the whole interval. So in this case, the Laplace transform of ft is given by the Laplace s times the Laplace transform of ft minus f0 minus the sum from k equal to 1 to m e to the minus tks f of tk plus minus f of tk minus. So these are again jumps at the respective point t equal to tk. So this is the general formula for when you have finitely many jump discontinuities. Now for B, which is discontinuity, f has a discontinuity, ft is discontinuous at t equal to 0, but the limit t tends to 0 plus ft exists. So in this case, the Laplace transform of f prime t is given by s times the Laplace transform of ft minus f of 0 plus, which is nothing but this limit here. And I'll just remark that if f prime is piecewise continuous on the whole interval 0 infinity, then this limit exists. So this is an application of the fundamental theorem of calculus. Theorem of calculus. So I urge you to prove these formulas by yourself using the definitions very carefully, and it's not too difficult to show these. So now I also should note that all formulas above are valid for s greater than alpha, where alpha is the f was assumed to be of exponential order alpha. So now the third one is higher derivatives, and this is a very important property, because this is the property that will help us solve ordinary differential equations. So the question is to compute the Laplace transform of the nth derivative of f. So the formula for this case is, so before the formula I have to assume some things. So assume that f t, f prime t, f double prime t, and so on up to the n minus first derivative of f are continuous on the whole interval 0 infinity, and fn t is piecewise continuous. So I should also assume that all these derivatives up to the n minus first power are of exponential order and continuous on the whole interval 0 infinity, and the nth derivative is piecewise continuous on the whole interval 0 to infinity. Then the Laplace transform of the nth derivative of t is given by s to the power n Laplace transform of ft minus s to the power n minus 1 f of 0 minus s to the power n minus 2 f prime of 0, and so on up to the last term, which is nothing but f of n 0, and we continue up to the last term, and in the end we will get the n minus first derivative of f evaluated at 0. So here also you can assume that f, f prime, and all the derivatives up to n order n minus 1 may not be continuous at 0, and they can have discontinuity at t equal to 0, but the limits should exist, and in that case, in case f, f prime, etc. up to fn minus 1 t are discontinuous at t equal to 0, but these values exist at 0 when you take the limit as t tends to 0 from the right, then the corresponding formula is simply given by the same formula, except that you have to take the limits for each of these terms, where you had f0, f prime 0, fn minus 1 0, you have to take f0 plus, and then you have to take for the second term f prime 0 plus, and so on up to fn minus 1 0 plus. So these are the formulas for the Laplace transform for higher derivatives in these two cases. So now let us look at an example for the application of this formula for higher derivatives. So this example is given by the function fn of t, which is exponential t over n factorial, and you take the nth derivative dtn of the function t to the power n e to the power minus t, and this is for n equal to 0, 1 and so on. So for each n you will get a function, and these, it turns out that these are always polynomials. These are polynomials, and these are called Laguerre polynomials for each n. So the problem is to compute the Laplace transform of f and t. So suppose that we denote by y our function yt, our function t to the power n e to the power minus t. So then f and t is simply e to the power t over n factorial and the nth derivative of y. So the Laplace transform of f and t is 1 over n factorial, and you take the Laplace transform of e to the power t of the nth derivative of y. So if we can compute the Laplace transform of the nth derivative of y, then we can deduce what is the Laplace transform of e to the power t times the nth derivative by the first shifting theorem. So it suffices to compute just the nth derivative of y. So for this we will use the higher derivative theorem. So the Laplace transform of the nth derivative of t is s to the power n, the Laplace transform of y, and then you have these terms Sn minus 1 y0 minus Sn minus 2 y. Now note that these are all polynomials, so they are all continuous at 0, so y prime 0 and so on, s, and the last term will be the n minus 1 derivative of y at 0. Now notice that yt is t to the power n exponential minus t, which means that if you compute, let me go to a new page, if you compute y prime t, this is n t to the power n minus 1 exponential minus t plus t to the power n minus 1 times exponential minus t. So when you differentiate once, you still have a coefficient of t on both terms, which will make the derivative 0 at t equal to 0. So at t equal to 0, y prime t equal to 0. So since we are only differentiating up to n minus 1 terms, so let's look at the formula again. So we are differentiating up to n minus 1 terms, but for each one of them you will have at least one term, at least the first power of t will appear in all the terms. So in fact all of these are 0, all of these terms are 0, so you only get the Laplace s to the power n times the Laplace transform of yt. So this implies that first of all that let me write yk at 0 is 0 for k equal to 1, 2 up to n minus 1, and so the Laplace transform of the nth derivative of y t is simply s to the power n times the Laplace transform of y. And now we can directly compute the Laplace transform of y. So this can be computed in two ways. One is we know what multiplication by powers of t look like, the Laplace transform what they look like. The other is simply again by a shifting theorem, because this is shifting by e to the power minus t, so it's shift by plus 1. So we know the Laplace transform of t to the power n, which is n factorial over s to the power n plus 1, but it is shifted by plus 1, so you will get n factorial over s plus 1 to the power n plus 1. So now we can determine the Laplace transform for the Laguerre polynomial, and this is 1 over n factorial times the Laplace transform of e to the power t and the nth derivative of y evaluated at s. But by the first translation theorem, this is equal to 1 over n factorial, the Laplace transform of the nth derivative of y evaluated at s minus 1, and we know that the Laplace transform of the nth derivative of y is s minus 1 to the power n. So because we are evaluating at s minus 1, so this is s minus 1 to the power n times the Laplace transform of y t evaluated at s minus 1, and this is nothing but n factorial over s minus 1 plus 1 to the power n plus 1. So this n factorial and this n factorial cancel out, and you are left with s minus 1 to the power n by s to the power n plus 1, and this is valid for s greater than 1.